just so you can feel
Yeah.
intelligent.
Yeah.
Okay, I got
Okay.
305, so let's get going.
Okay. Cool.
Welcome back, everyone. My name is Rohit, if you guys don't recall. And I'm joined with Ricky Hugh as well as Zoe Hugh. Welcome to session two. Today, we're going to be talking about data for artificial intelligence and getting some perspective on what data actually is and what you should think about it as. Just like last week, Ricky's going to lead through the discussion. No Prash this week. He'll join us next session. Zoe and I are going to moderate the chat. So if you have any questions, feel free to type them in the chat and we'll respond to you. Ricky might take a pause and ask you something specific. These server sessions are fun when you're engaged and asking questions. No question is dumb. We accept all questions. But without further ado, I'll turn off my video and mic and pass it over to Ricky Hugh.
All right. Thanks, Rohit. For those of you who don't know me, I'm Ricky. I'm a second year med student at Queens. Previously did a master's in artificial intelligence. Today, there's no Prash, so he's away today. I'll be taking over most of today's session. He'll be back next week and he'll talk about machine learning. And he'll take over most of next week, and he's great for that. So today is really about data science, and data is a really important part of machine learning. There'll be specific applications of data geared towards machine learning, but most of the principles you see here are applicable to any data science study, whether you're doing a retrospective analysis on medical records or anything. And there's two objectives here today. First, I want to instill some skepticism for you to critically think and appraising data, especially ones you see in social media. And the second is to learn how to prepare data properly for machine learning. Famous quote: a lot of things you see on the internet are fake, quoted by Abraham Lincoln. That's a joke for the record. So we'll go over some boring biostats prereqs first, and then I'll go over some common pitfalls we see, and that'll segue towards how to avoid these pitfalls to prepare data for machine learning. And lastly, we'll touch on two steps that we do in almost every machine learning task, which is an exploratory data analysis, and then making sure our machine learning project is generalizable. So here's a motivating example. You see, there are 12 different data sets here, right? And they're all visually different. This star is definitely different from this ellipse. But I can come up to you and say, hey, I got 12 data sets. I fit a model to it. Everything has exact same mean, exact same standard deviation, exact same Pearson correlation coefficient, exact same odds ratio, right? But these data sets are obviously different. So what's the deal here? Well, these stats, they don't tell the full story of data, and a lot of times they mislead us. They're very useful to gain an initial insight, but we have to do some additional investigations to properly appraise the data. So data is abused a lot these days by social media companies, by companies that want money. They say like, hey, our pill gives you a 200% increased chance of building muscle. Well, if your base probability is 0.00006, that increase is meaningless. And unfortunately, even some scientists and some publications, they sort of mislead with data. So data is a poor guy here. And just when you think data hasn't had enough, in comes politics. Politics really performs a Kurt Angle suplex on the data. If I had a nickel for every time some sort of political statistic was misleading, I would be able to afford rent in Vancouver. Right. So here's an example. This is a federal judge. I'm not going to say which country and where, but they're saying that, well, we can understand why people don't fill forms by performing a regression analysis that would disaggregate the potential cause to identify 95th percentile degree. He's spewing a lot of words, probably really fast in this interview. He's throwing like regression analysis, 95th percentile. But when a data scientist looked at this interview, they said, hey, this doesn't make sense. You would not use a regression analysis for this purpose, right? But a lot of people in the public just absolutely ate this up and like, wow, this is so smart. This is such a great idea. So here, I'm going to introduce you to this data set. I'm going to talk about this data set a lot just to pull up some examples. So pretend we want to build a machine learning model that will predict if certain hockey players will develop group A strep. So this is the outcome that we want to predict. And this is the data that we have. We have the hockey players' names, what division they're in, their oral temperature, their age, whether they have exudates, pus coming out of the tonsils, and whether they have swollen lymph nodes. Now, I'm gonna name some definitions. So these columns, like division, oral temperature, age, these are called features, right? Sometimes people call them variables or characteristics or descriptors. I really don't like descriptors because it's really vague. Features is the common word for these. So age is a feature, right? We want to take the average of the age feature. That's referring to a feature. Whether they have group A strep is an outcome, right? Or it's called the ground truth. If we know what happened already, this is what we want to compare our model to. Uh, Peter is asking cough. Yeah, cough is also part of the analysis. I've excluded a lot of things in the Centaur and McIsaac score in this, but this is just for demonstrating some definitions. So each individual patient, let's say Steven Stamkos, this we call it an example or a sample. Some people call it an item. I don't like that. That's also very kind of misleading at times. Usually example or sample is what we call this. That's just to give some common terminology to discuss with. And we'll go back to this later. So to go through some biostats prerequisite to analyze this, this is the hierarchy of evidence. So at the very bottom are ideas, editorials, and anecdotal. Like say, an expert says being in the Atlantic division increases your chance of contracting group A strep. And then then you have case reports, cross-sectional studies. You don't have to know the exact mechanism of this. Just know that up on the top are randomized controlled trials where you actually perform randomization. You have a control group and a comparator group, and then you look at the difference between the two. And at the very top is a systematic review or meta-analysis where they aggregate usually a lot of randomized controlled trials and they look at statistical significances. So evidence gets stronger as you go up this hierarchy. But the problem is that the way data is handled these days, especially in social media, there's a huge focus on editorials and anecdotal evidence. So I just searched, the hot topic right now is COVID. I just searched COVID on news aggregate site, and it's always like, well, medical experts say this will happen. Medical experts predict this will happen. Medical experts warn that this will happen. Now, don't get me wrong, expert opinion is important, especially when we don't have the meta-analysis, but it's at the very bottom of that hierarchy. So we have to be very critical when this comes. We have to appraise it. Is their opinion supported by statistical evidence? What sort of data science are they using when they formulate these opinions? Usually they're not. It's just for the purpose of a quick interview. People get medical expert opinions. So the question is that where does machine learning stand? Because machine learning isn't really a randomized controlled trial most of the time. You're not always recruiting patients that are in a control group or comparator group and then apply some machine learning treatment to them, right? So the answer is that it really depends on how the study is designed, but most machine learning studies, they look at cohort, they look at entire population, they look at what they're exposed to, and they look at the outcomes, and they try to build a model that predicts the outcomes. For instance, there's some RCT elements of machine learning in that we try to blind the machine learning model so that it's blinded to who's receiving what exposure and who has what outcome, but it's not really a randomized controlled trial in the classical clinical trial sense. This definition really it's not that important. It doesn't bog any machine learning progress down. It's just nice to keep in mind of this hierarchy. Now there's two sort of categories of statistics. One is the classic descriptive stats. That's when you calculate the mean, standard deviation, and spread of the data. Let's say the mean age of our patients or the spread of the age of our patients, right? This is saying we just want to get some insight of what our stats are. We want to just say something about the current population that we have. And then on the other hand, there are inferential stats. This is when we want to take this data and we want to make some conclusions, like say, well, this variable is very, very important and predictive, right? Or we want to say that, well, our machine learning algorithm can take these variables and predict an outcome. We can take all the hockey players and predict who has group A strep based off all their features. So the question is, where do things like p-values, analysis of variance, and odds ratio lie? Because the way I'm talking about it, it makes it sound like they're sort of descriptive stats, right? You're just computing a p-value. That's just a feature of the data. ANOVA is just the difference in variances between two data sets. So the answer is a bit complex. Okay, sorry. So I'll go with an example. So let's say we have our hockey players again, and let's say we're looking at only tonsil exudates. We're only looking at this feature. So this feature has an odds ratio of 2, right? If you have tonsil exudates, you're twice as likely to have group A strep than if you don't have it. So is this an inferential statistic, or is this just descriptive, or is this predictive? Now, a lot of people argue, especially in classical statistics, that these are inferential statistics because you're concluding that this feature is very, very important for predicting things. But my answer is sort of. It's inferential in that you're making some sort of conclusion, but you're not really making a conclusion that's verifiable. You're not, you don't have a performance of your conclusion that we can try validate with some accuracy metric. So to be really, really, really inferential, you have to use this odds ratio and let's say build a prediction model. Let's say you have some input data and you have your odds ratio model, and then you have an output prediction. Because then you're concluding that, hey, we're taking this data, we conclude that these odds ratio are really, really important, and we're going to prove it by having some sort of prediction accuracy. So that's fully, fully, fully strong inferential. Sometimes this is just a technicality, but it's good to keep in mind because we see a lot of studies where they just report odds ratios. And the question is that as data scientists, how do we interpret this? And where does machine learning have a place in this? So for instance, we're comparing the odds ratio of using different drugs or IVIG for strep A infections. And they're reporting the odds ratio, right? They're saying like, hey, using clindamycin without IVIG has a greater odds ratio of toxic shock syndrome. Well, it's giving us good insight into the data, but what's their conclusion? Are they concluding that you should use this? If we do use this, we can validate it that it has a 95% chance of preventing toxic shock syndrome. So that brings me to the point of machine learning's purpose is to try and be predictive. You're trying to accomplish some task that can be verifiable. And that's a full inferential statistic method. So this is the elephant in the room, talking about p-values. It comes up all the time. I get this from reviewers all the time. So I like to clarify what it is in case you really have to use this understanding. So a p-value is simply the probability that your data and your results satisfies the null hypothesis. I hate this definition. There's a sort of simplified way of thinking it, which is the p-value is the probability that your data does not support your hypothesis. So we think of this commonly in a randomized controlled trial, and I'll tie this into machine learning in a bit. In a randomized controlled trial, usually our hypothesis is that, well, there's a difference between some outcome we measured when we provide a treatment. So let's say we measure the survival of patients before chemotherapy, and then we measure the survival of patients after chemotherapy. And then we do something like a t-test or something, and we see our p-values under 0.05, which interestingly is an arbitrary threshold made about 120 years ago, but it's still useful. It's a useful insight. So I'm not knocking on it too hard. Well, we see there's an obvious difference between these two treatment groups, right? So in this case, a p-value is very, very valuable. It shows that there's a significant difference between two groups. So the question is that in a machine learning algorithm, we don't really say have a group that we treat with a machine learning algorithm and a group that we don't treat, right? We take that entire data set and we try to make some prediction. So for really strong inferential statistics, what is our hypothesis that we're trying to use a p-value to validate? For instance, if our machine learning program is to predict whether hockey players have group A strep, what's our hypothesis, right? It's not that hockey players before and after machine learning will have different probabilities of having group A strep. So our hypothesis could be that our prediction model is better than random chance. In that case, we'll compare our predictions to a series of random predictions, and then we'll use a t-test, which tells us that they are statistically significantly different. Or our hypothesis could be that our prediction model is better than current practice. So then we have to compare our prediction results with the results of current practice and do a t-test and say, wow, okay, they're different. So here's the problem. P-value is not a strong enough validator. T-tests just say they're statistically significant difference. But we don't just want our machine learning model to be different. We want it to be really, really good. We want accuracy of 90%. We don't just want different from 60%. Instead, we have a lot of accuracy measurements to measure performance of machine learning models, like sensitivity, specificity, dice coefficient, Hausdorff distance. There's a lot out there. But what to know is that when it's high accuracy, it's high dice coefficient, and we have enough samples, we already know the prediction is not going to be random to have that accuracy. So you'll see in a lot of machine learning talks, papers, journals, we don't really report p-values. They're really, really important for a randomized controlled trial, for instance, and they're really, really valuable. I'm not knocking on it. Just that we have to understand what p-values are to know if they have a place or not in certain applications. A lot of times reviewers still ask me for like p-values, and I'm thinking, this is just not applicable in this case. So I just simulate some data to prove that it's statistically different from random chance, and they're happy. So if you're ever in doubt whether you need to include a p-value or not, just look at similar papers to your project or application and see how they validate accuracy. So on that note, I'm going to take a small 1 to 2 minute break. That's a lot of boring prereqs. If you have any questions at all, feel free to ask in the chat or speak up. While I draw a meme. Is the fact that something is different important, therefore p-values important? Yes, it is important. It's very important that things are different. The question is that what are we comparing to that's different? In a randomized controlled trial, we're comparing a control placebo group to a comparator group. So it's very important that we elicit that there's a difference. In machine learning, let's say we have, for all the players, we have a prediction of whether they have group A strep or not. So what are we comparing our predictions to? That is the question. So we could compare our predictions to, let's say, the current practice, the current model, and then we can calculate a p-value saying that, hey, it's now different. So we can, p-value is an important first step. It's an important sort of bar to cross to say that our results are statistically significantly different. But usually we have much, much stronger validators, like in accuracy measurements. If the accuracy of our prediction is 95%, it's very, very, very likely, almost guaranteed that it has an accuracy because we're doing something statistically significantly different. So you can always report p-values, but understand that it's sort of a low bar when we're doing machine learning algorithms. Okay, give 30 seconds for any other questions before moving on, while I take a drink. Yeah, they do have less of place in machine learning papers, unless it's a machine learning papers that is set up like a randomized controlled trial where you apply a machine learning treatment to a placebo group and a control group. Can you clarify the tonsil exudate? Okay, last question, then I'll move on. The tonsil exudate example. So the exposure variable not be the strep XSL. So this is where I'm defining this as the outcome and the tonsil exudate as the exposure. So the exposure is something that changes an independent variable, and the outcome is your dependent variable. We want to see how the outcome changes depending on how the patient is exposed to your independent variables differently. So here in the odds ratio, we're saying that we want to see how much more likely someone has group A strep if they have tonsil exudates or not. Is that okay? So I'm going to move on. So now I'm going through some pitfalls and common problems with data. So this is fun. I love this because it makes everyone skeptical of data before I sort of bring our hopes up back. So the first thing is that the relationship between data and outcome is especially in biology, is complex and it's nonlinear. What do I mean by nonlinear? For instance, if we have an odds ratio of age being 2, we're saying that age increases your odds of group A strep by a factor of 2. But what if the probability between 2 and 5 years old is different from 50 and 53 years old? We know people develop much more extremely between 2 and 5 than between ages 50 and 53. So there's a nonlinear relationship between age and group A strep, but odds ratio is a linear calculation, so it doesn't capture that relationship. Second pitfall is that a lot of features are not independent. For instance, if we only look at the odds ratio of age, well, what if people age 23 in, let's say, Toronto versus people age 23 in Edmonton? What if they're exposed to different, what if they're part of different endemic regions? They're exposed to different amounts of group A strep just because of geography. Well, they're here, even with the same age, they're exposed to something different. So these variables are affected by confounding variables, which a lot of models won't be able to capture because they, like an odds ratio, it just looks at just this variable. Another problem is that sometimes data is not detailed enough. We see this a lot in old clinical papers, especially 50 to 60 years ago. For instance, if we're looking at tonsil exudates, well, if you look at the criteria right now in our family medicine guidelines, it's whether you have tonsil exudates or not. What about the amount of tonsil exudates? What about the location of the exudates? What if it's from one tonsil or two tonsils, right? What if it's a huge amount of pus coming out? Does that change the diagnosis? It was difficult back then, understandably, to characterize this. I'm not harping too hard on the current guidelines. It's the best we've got so far. But with machine learning, maybe we can look at this in more detail, right? Maybe we can look at geometry. Maybe we can look at varying amounts. Sometimes the data we have is a lagging predictor, and this is less of a statistical problem than a practical problem. For instance, lymphoadenopathy. What if by the time your lymph nodes are enlarged, it's already days past when group A strep is detectable? What if tonsil exudates comes before your lymph nodes are being enlarged? How do we analyze the time dependency of these variables? And is this useful? Because if lymph nodes being enlarged is such a late predictor, do we want it in our model if we want the purpose of our model to be an early screening tool? The answer is probably no. So this is always fun. So in COVID-19, the statistics that always gets reported in the news is the number of cases a day. This is the number of cases in the United States. But even from this, I bet all of you can see some problems, right? Everyone's saying, hey, our cases are dropping, or hey, our cases are here, our cases are rising, we're doomed, right? Well, number of cases depends on a number of things, right? Depends on your number of tests you have available. A lot of confounding factors, right? Number of cases depends on whether a county will report it or not, right? What's we look at instead a lot of times is number of hospitalizations, right? Because this one, we can't, if someone's hospitalized, likely people that need to be hospitalized will get reported as being hospitalized, at least more so than people being tested. But the problem with hospitalizations is that this is also a lagging predictor, right? It lags by about 2 weeks. So that's what makes COVID-19 a very difficult problem to present to the media, especially to the public, because they want one sentence of one eye-catching statistics, which they use number of cases by day. But number of cases is affected by a lot of confounding variables. Now, a common method that we use, especially in medicine, to develop predictors is that first we do some descriptive data analysis. We look at the features, we calculate correlation coefficients, odds ratios, a p-value of that odds ratio to see which variables are what they call predictive, which variables or features have high odds ratios and are more likely to be correlated with an outcome. We then take that and we make some sort of scoring system, right? Let's say if your tonsil exudates, you have tonsil exudates, then you have an extra point. If you have lymph node swelling, you have an extra point. And you have points above 4, we're going to give you penicillin. And then someone evaluates the scoring system based off some clinical outcomes to measure its accuracy. And this is what we have so far in your family medicine courses. We have the center score, or I think more recently we're using the Muck-Isaac score. But for instance, fever gives you 1 point, absence of cough gives you 1 point, lymphadenopathy gives you 1 point, exudates gives you 1 point. And they found that these, in the original paper I saw, these are high odds ratios features. But when you actually look at the statistics and the accuracy, it's not that great. It's still very, very useful for screening, but it doesn't give like 95% accuracy, which is what a lot of machine learning models are trying to do. So there is a lot of limitations in this sort of approach. So the question is that hypothetically, if none of these variables are only associated, but do not predict likelihood of group A strep, can you still say that a machine learning algorithm built from this system is predictive? Oh, if all the variables are only associated and do not predict likelihood. So I'm going to be a bit pedantic with the terminology. So the word associated is a very strong word. It means that there's biological plausibility, there's a temporal effect. So I'm going to say if the variables are highly correlated but do not predict the likelihood. I think that's what Kai is trying to ask. Can you still say a machine learning algorithm is predictive? I would say no, because predictive means that we can evaluate it somehow. So if they're highly correlated and we build a machine learning algorithm and it has very, very poor accuracy, I'm not going to call it predictive. Predictive means the way that we use the variables will have a sufficiently high enough accuracy. So even if the correlation ratios are very high, if we cannot use them correctly, it's not predictive, it's not useful. So that's a very good question. I think the word predictive gets thrown around a lot and gets misused, but to be predictive, validate it with some accuracy testing. So this is the big take-home message from the last 5 slides. Odds ratios and correlation coefficients, they are useful. They are useful descriptively a lot of times, but they're not accuracies, right? You have to use them somehow and then measure the accuracies by making a scoring system. Right? That's why the center score has such a low accuracy when validated by a lot of different papers. It's still very useful because that's what we have. It's a useful screening tool. And the medical world is slow to adapt, but new machine learning technologies you'll see later on and in next week, and even in the program session where we build a machine learning algorithm, it sometimes gives very, very good accuracies, better than the current status quo. This is just another paper just saying that odds ratios are not accuracies. In your free time, you can take a read of this. This will be on the slides. So another pitfall is rely on correlations. So I'm going to claim that I can force a correlation with absolutely anything. So here's some data. Let's say the fit is this. We can see it's badly correlated. How it should look like is like this. The fit should look like this in the center. But I can make almost 100% correlation with something totally fabricated like this. This is just a high enough degree polynomial that goes through all the points. The problem is, you can see I'm sort of cheating here, right? I'm just abusing the nature of mathematics, polynomials, to go through every single point. But let's say, if you extend this polynomial, it will look like this. Let's say there's a new data point that's around here. I would not be able to catch it. If new data point's here, I wouldn't be able to catch it. But this model in the middle will be much better at catching those data points. So be wary of correlations. Okay, now with that, I'm going to take another 1 to 2 minute question break in case anyone has any burning questions before we move on to some applications specific to machine learning. Was there a term for that last example? Yes, this is called overfitting. And I'll talk about this in a few slides. It's a big, big, big problem. Can machine learning simplify functions to a level that we can understand it? That's a tough question. It depends how the machine learning model is built. Uh, Traditionally, the programmer defines sort of the range of the functions that learning model will take on. You'll understand this a lot more when we talk about neural networks. Um, but usually the functions, the mathematics of the functions, we give it a template for the machine learning model to adjust parameters. It'll never reduce for instance, if a function is, let's say, uh, something like this, it'll never reduce to something like uh, 2x. It'll never reduce something as simple as that. It'll always stay in this form, but the machine learning model may say add a few coefficients, or add some constants to adjust so that it fits the model better. So it'll never simplify a mathematical equation to that point. There's some really advanced machine learning unsupervised methods out there that build their own functions, but I won't talk about those. Will we be using PyTorch? We'll be using Jupyter. I'll give you instructions. So we'll be using the Jupyter Notebook framework on Python. We won't have to use PyTorch. We're just going to use sklearn. That's the library that we're going to use. I'll give you all the instructions in 2 weeks. It's quite easy to install. It should take about 30 minutes. At what level of complexity would you say, so this is the last question before I move on. What level of complexity would you say a machine learning model is required to build a good model? This is a cop-out. It depends on your problem. Because if your variables have very complex interdependencies, then your machine learning model might have to have multiple layers of mathematical functions. So to give you some perspective, the model I built to sort of predict where a placenta is on an ultrasound scan, that had about 1.2 million parameters. So it's the way to evaluate it isn't amount of complexity, it's the accuracy, especially accuracy tested on new data, which is a good segue to what I'm moving to next. So this is what I was talking about before. When you're sometimes if you build your entire model on your data set, that is an absolute cardinal sin in machine learning. You can get really high accuracy if I build any statistical model on the entire data set, and you'll get something like this, something that's overfitted. So super high accuracy, but when you add a new data point, okay, when this extends, it goes like this. When you add a new data point, it just is unable to capture it, right? You're unable to extrapolate to new data. That's when you build a model from all of your data. This is called, first of all, it's called overfitting, and you're also breaking the rule of cross-validation, which I'll touch on in a few slides. This is just another fun slide relying on correlations. This is per capita consumption of mozzarella cheese and civil engineering doctorates, right? It's almost perfect correlation, but we know it's bogus. Okay. And this all results in sort of what I call a tunnel vision conclusion. If we don't look at the full data set, if we don't look at all data, if we overfit to only our data, we would say like, hey, look, the Atlantic is having a strep problem. But there are a lot more Atlantic hawk players, right? We didn't look at everything. We're just basing off correlations, and we're making a bad conclusion. So the question is, how do we look at data now for machine learning? Machine learning is really good when to find out complex data relations, like predicting whether a tumor is malignant in an image texture. It's really hard for a human to quantify and explain what they're seeing on an image, but machines can do that mathematically. Or predicting what threshold amount exited is predictive. So for instance, a model might say that if your age is 24, well, then that changes your exit threshold to 60% coverage. And if your lymph node size is above this, then we predict that you have group A strep. So that level of detail is what we expect from a machine learning model. And that's the strength of machine learning. However, it's only as good as the data you give it. Some models have ways to sort of filter bad data, but don't always rely on this. Which brings me to the next point where you should always clean up your data. So first step, machine learning loves numerical data. For this string of letters, mathematically means nothing. What you can do is you can create dummy variables. For instance, whether a player is in the Atlantic or in the Pacific, and you give a 1 or 0 depending on which category they fall in. However, we need a lot of data, right? Right now, we only have 5 data points machine learning models need lots and lots and lots of data to find these complex relationships. Now, the question is, how much data do we need, right? So a lot of people don't like this question. I don't mind this question. The answer is always as much as possible. The rule of thumb, which is contentious, but we sometimes go with, is at least 10 times the number of features. So back here, we have 1, 2, 3, 4, 5, 6, 7 features. So we want at least 70. But really, like 700 is a lot better. So if you want your publication to be absolutely game-changing, like changing a guideline, like the PCARN model for pediatric head injuries, they use over 5,000, I think like 7,000 images and patients, and they change the game in guidelines, right? If you have, let's say, an innovative way to look at data, like a neural network to look at ultrasound images in a new way, you can get away with lower numbers and still publish, right? So the amount of data there's sort of a loose range. Okay, so you see what I did earlier? I expanded the dummy variables, but that also increases the data demand, right? I just created a whole separate feature category. So that's a good question by Kai. How do you prevent overfitting? Through cross-validation, which I'll talk to in a bit. So another trick we can do is data augmentation, where let's say we want to predict whether this thing's a cat. Well, we can slightly rotate it or move it, translate it. You see, it still keeps the key feature of a cat, but it's sort of different data. It changes that mathematics of that picture. So it's sort of simulating more data. And this is a trick you can use a lot of times in images and videos, not so much in clinical variables. There are different ways to also look at data. Some sort of features you might not know of are statistical intermediate calculation. For instance, entropy is one. Right? Entropy tells you how unexpected data is. This is a gallbladder ultrasound, and this is a gallstone. So if we look at the direction, so this is skin here. If we look at the direction of the scan, we notice it gets dark, 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 and suddenly bright. So this will be very, very high entropy. I think sigma is the same. It's very, very, very high entropy, right? You don't have to know this. This is just to give you insight of what's out there. Another way, this is an electrical engineer's favorite. Half my electrical engineering training was focused on this, is a Fourier transform. That's when you change your data to the frequency domain. And the theory is that any sort of periodic signal you can decompose to sinusoidal components. You see this wave? Well, it's actually made of 3 sinusoidal waves, right? And a Fourier transform gives you the magnitude of those waves. So in medicine, EKGs, ECGs, that's what we think of when we're doing this, right? Your heartbeat, your sinus node gives a periodic signal. So we can sort of break down ECGs this way. And we can insert these features into a machine learning model. Okay. So there's a step in machine learning we always use, which is exploratory data analysis. It's to first take a first glance of the data. This is when we use the descriptive stats like mean, range, everything. And we also want to only keep the variables that have biological plausibility. This is another fun example of bad correlations. For instance, we would throw out one of these variables because it's just not related. So we want to check that the range is sufficient. We want to check that the features are varied. If everyone has the exact same feature value, it's useless. Another thing we want to do is remove collinear features. This means features that represent the same thing, like weight and BMI. We know those are related by really, really, really closely. So usually that's removed in machine learning models, not always. So we do this by computing the variance inflation factor, which is this equation here, but in Python, you'll see it's just this one line here. So you can see that you don't really need to know the math to use it. It's good to have insight, but you can still use machine learning by being resourceful and looking at programming references. So there's sometimes there are too many features. We don't have enough samples. So we do a first removal of features that have low statistical significance. And this is where we bring in the odds ratios and correlation and ANOVA, and we remove values that have low p-values, which means that the basic analysis doesn't give a statistically significant result. We might not throw this into a machine learning model, right? We do this out of desperation sometimes. A lot of machine learning models have this built in that'll do this for us, and we want to throw as much data into it as possible. But sometimes, like with logistic regression, it doesn't do well when you put way too many features in it. So here we're looking at, this is an example. I'm looking at the p-values here. I only have n equals 70 in this data set, so I had to remove some. So I'm removing the ones with very, very bad p-values. Now, this is the last topic, which is on generalization. This is Kai's question, right? How do we make sure that we don't overfit, that our data can be applied to new data? Well, one technique we can use is make sure our data is from a varied source, right? We want patients with different ethnicities, different ages, from different locations in case there are confounding variables. We want to recruit as much, as high amount of samples containing confounding variables, because when there's enough, then the machine learning model can discern between them. A lot of papers get away with this without doing this by, let's say, looking at a data set from a single institution or a single age group, and they also have high accuracies, but they cannot claim that this is generalizable and this can be FDA approved, for instance. They can just claim that, hey, it's a proof of concept, it works for this data set, we're going to expand it further in a further clinical trial, right? Another big idea is cross-validation. This is really the big topic. So this is a technique to make sure that our data is not overfitted. What we do is that we take our data set. For instance, this is an example of five-fold cross-validation. We split it into 5 sections, right? We take these 4 sections and we use this to build the model. So the model just does not use this data at this last section at all until when we're verifying the accuracy. Then we test it on this last section. Let's say we test the sensitivity, specificity, or area under the curve, whatever accuracy measurement you want. So in a way, the model is blinded to this new data so that we're not overfitting on that entire data set. In a way, it's sort of, this is like new data the model is seeing. This is as if new data comes in and we're testing the model, right? And then we can repeat this. So if we're doing 5-fold cross-validation, there are 5 segments. So there are 5 subsets we can insert into the testing set, right? And then we take the average accuracy. So in this way, we repeat trials, repeat what's blinded, rebuild the model, and show that, hey, it works no matter what sort of new data we're throwing at from our data set. But keep in mind, if your data all comes from one institution and let's say 1 day of clinical data collection, all this will be similar data anyway. So it's important to keep that previous point to have varied data as much as possible. So the big takeaways for today is always be critical of descriptive stats, right? They're not very strongly inferential a lot of times, and sometimes it's misleading. Get as much data as possible for your machine learning model. If you have 10,000 data points, that's amazing. I will be salivating to work on that and publish a high impact journal. Clean up your data if you have to. Remove collinears, change categorical to numerical. Sometimes remove the ones without biological plausibility up to your judgment, and always, always, always use cross-validation, right? Use cross-validation to ensure your data has some degree of generalizability. Okay, that's all I have today. I hope this is useful, and these are some really important takeaways that will segue really, really nicely to Prash next week when he talks about machine learning. And this sort of data analysis and insight serves as really strong guidelines on to prepare data well for a machine learning algorithm. So at this point, I can take any question. I can stay and take any questions from the chat. So the question is, what factors influence how you split the data? So that's a very, very good question. Very good question. So the honest answer is convention a lot of times. There are some papers where they try to measure the area under the curve depending on how you split the data, and they have a bunch of simulated data sets, and they found that so this is an 80-20 split, right? Right. They found that 70-30 also works. 60-40 is okay. 90-10 is not that great. So this is about the range by convention most machine learning papers and most machine learning projects do. You're not going to get harped on. You're not going to get rejected just because you use a 70-30 split compared to an 80-20 split. A lot of times people use 80-20 because it divides into 5 nicely. If you use 70-30, you're gonna have to have 10 k-folds, right? Because you can't divide by 2 because of 73 is the lowest ratio you can get with common factors. Yeah, that's also a good point by Rohit. Size of the data set. Um, if your data set is too small, you can't split into too many k-folds. You might have to use a different strategy. Okay. So, any other questions? Feel free to type in the chat, or even feel free to speak up. So that's a good point, to ensure your data is similar both in your test and training set. So in your test set, let's say we only have one group A strep, whereas in each training set we have 10. Let's say this guy has 12, this guy has 30, and this is 40, right? Then our test set is not that useful. We only have one positive outcome in our test set. The predictions, if we can predict every negative correctly, but we absolutely fail at positive predictions, this will still have like a 99% accuracy, which is not representative. Okay. Class imbalance, yeah, class imbalance will also impact your decision. So what we usually do, we try to make sure that first, our whole data set, we have a large enough n, and that within that data set, there's a sufficient number of positives. So let's say if we have 10 patients, and let's say 2 is positive and 8 is negative, we won't be able to make a good split. But if we have let's say 10,000, and even if 2,000 are positive and then 8,000 are negative, we can still have hundreds of people in the positive branch. So having a high enough n does help prevent that really stark differences in accuracies due to imbalances. But ideally you want an even split. That's the best way. 5,000 positive and 5,000 negative. So again, summary today. Descriptive stats, a lot of linear odds ratios are misleading. You need a high enough n. You try to make sure it's balanced. Right? You want to pre-process data really, really well for your machine learning algorithm. And you want to always cross-validate your model, usually with an 80-20 or 70-30 split. And you want to make sure those bins have enough outcomes in both categories.
Cool. Well, one last question.
Okay. AI can be used to create new functions. We don't, yeah. Okay, for sure. Do I have I don't have an empty slide. Okay. I'm gonna look for a sort of empty slide. Okay. So AI creating new functions versus AI adjusting functions. So for instance, one AI algorithm is to use a logistic regression. You have some sort of base function that looks like this, right? And let's say you want to use this curve to model your data. Your data is something like this, and you want to adjust this curve. What the AI will do, it'll start to add weights onto here. Let's say alpha plus beta, maybe add another weight here, right? And it'll adjust these parameters so that the curve fits really, really well to this data set. So this is a logistic regression AI model. So in this case, the AI programmer has specified that this is the model I want to use. So the AI doesn't have a lot of freedom to adjust this function, right? It can only adjust these parameters in this equation. Now, in the case of for a neural network, an AI will have a little bit more freedom, right? A neural network, the architecture looks a bit like this. Yeah, this is sort of a more advanced question, but I'm happy to answer this. And this is the output, right? One neural network. So what each individual node here has some sort of mathematical function. It can even be like this regression function up here. So what a neural network can do, it can totally just say that, hey, this node is completely useless. This function is completely useless. We're gonna absolutely nix it, right? So then your output equation is gonna be it's going to be this function, these two functions, this function, and this function. So four functions in total that are sort of composite functions of each other. Sorry, g of h, I of x, right? So in this case, you sort of create this function that excludes other functions in your model. So this is still sort of constrained because you're only restricted to whatever is available that you defined available to your AI model. Your AI model will just remove the ones that are not there. So there's an even more liberal way an AI model can create new functions. And this is usually through unsupervised learning. So that's when you just give some data. Let's say I have this plot of data, and you're given some mathematical functions for the AI to explore, but you're not saying I'm going to restrict you to these, to like 5 or 6 of these. You can modify them anyhow you want. And the AI will say like, okay, well, I'm going to try this function. It doesn't work really well. Okay, I'm going to try this function. It doesn't work really well. Well, this one works really well. So right, and you don't give the AI any sort of ground truth or outcomes to measure accuracy with. You just let the AI go wild until the AI feels like it has found a meaningful relationship. And usually this gives the most creative, most original functions that AI creates. Right? This is part of a branch called unsupervised learning. So Prash will talk about this a lot next week. But still, it's still limited to, let's say, a library. You can still define a library of functions that the AI has to choose from. So that's how an AI can sort of create new functions and create new mathematical relationships. Sorry, that's a kind of math-minded answer. It'll be more apparent next week. Is there no way to reduce? There is a way to reduce the complexity. You can sort of set bounds of what it can choose from. You can sort of set bounds, say, hey, I don't want any functions that have more than 5 layers. I don't want any model that have more than 5 layers, right? So that's how you can sort of force sort of boundary conditions on these models. But it's usually a very complex task, and it's not well defined what the best way is to do so. Will supervised learning be more susceptible to overfitting? So it's a very strange answer because unsupervised learning means that we don't have labels, we don't have outcomes. For instance, going back to our original data set, let's see if I can get back there. Okay, unsupervised learning would be that we don't have this column at all, right? We're just trying to find relationships between this. So does that make it more susceptible to overfitting? Well, if we use it on all the data and we don't cross-validate and we don't do any of that, then the relationships, if fine, will be overfitted to this data set for sure. But if we cross-validate, if we only take, for instance, this 60% and build a model, then there's no clear answer. Is it going to be more overfitted to this or not? Because it could still create a really highly generalizable model if you choose and clean your data really, really well. It's harder to verify it compared to having the outcome column, but it's not absolutely more susceptible to overfitting, I would say. So I wouldn't worry too much about unsupervised learning. In medicine, it's not used that much. It's just good to know what's out there.
All right. Well, in the interest of time, I think we'll wrap up there. Thank you very much, Ricky, and thanks for everyone for being engaged in that chat. Just a reminder, if you haven't joined the Slack channel, please do. You can ask us questions there. This video will be recorded and posted, as well as the slides. And then we'll see you next week, same time, different instructor. Prash will be here. Otherwise, thanks, everyone.
All right. Next week's going to be fun. It's going to be on machine learning specifically.
It'll be the real deal. It's the stuff you don't want to miss. So,
yeah. All right. Thanks, everyone, for joining.
Bye, guys.
Hope you all enjoyed.